the current flows from the source through to the drain. So your gate, like the name suggests, is the one that determines the width of the channel. So these are your substrates, your P at the extreme ends. Those are your substrates, and that's your channel. So you get your current to flow from the source through to the drain, depending on the width that we have. So it's important that we have enough a passage here for the charges to flow, and we control that by the method of biasing. So you have, it's a 3-terminal device. That's your gate, that's your source, that's your drain, that's your depletion region, which offers resistance to the flow of current. So we need to keep this minimal, because should it be big, you'll get your channel to be obstructed. Okay, and this is an ohmic contact, which is what also contributes to this high input impedance, which was mentioned on the previous slide. Okay, so I've already mentioned that there are two types. You have an N channel and a P channel. So if here you have P, then your substrates will be made of an N material. Hence, it will be a P channel JFET. Okay, the 3 terminals I've mentioned, your drain, your source, and your gate. Okay, the JFET operation can be compared to that of a water spigot. The source is the accumulation of electrons at the negative pole of the drain source voltage. The drain is the electron deficiency or holes at the positive pole of the applied voltage. So at the drain is more positive than the source. Hence, you get the electrons to move, to be attracted from the source towards the drain. The gate controls the width of the channel and therefore the flow of charges from the source to the drain. As I mentioned on the previous slide, that the gate is the one that controls the width of your channel. So your electrons will be attracted from the source through to the drain on the channel, depending whether your channel is made up of P or it's made up of its N material, so whether it's made up of your electrons. So that's how the current flows. The current flows from the source to the drain. JFET operating characteristics. There are 3 basic operating conditions for a JFET. Your VGS is 0, your gate source voltage is 0, whilst VDS increases to some positive value. VGS less than 0, VDS at some positive value, voltage controlled resistor. So your initial working condition is that your VGS is 0. Like for instance, for your BJTs, if I may compare it with it, you know that for a BJT to function, you need to have a volt drop of 0.7 across the base emitter diode. 3 things happen when VGS is 0. And VDS increases from 0 to a more positive voltage. So again, we have an N-channel JFET here. We have our P substrates there. Can you see that the width of the channel is quite narrower because of the substrate? So we need to control through biasing. The way you connect your battery externally is the one that will determine whether your depletion region gets narrower. You remember even for BJTs that the depletion region needs to be as narrow as possible because it offers resistance to some flow, to the flow of electrons. So the size of the depletion region between the P-type gate and the N-channel increases. Increasing the size of the depletion region decreases the width of the channel, which increases its resistance. So if resistance increases, you'll get less charges to be able to flow from the source to the drain, which means less current. Even though the N-channel resistance is increasing, the current from the source to the drain through the N-channel is increasing because VDS is increasing. VDS is here. So by increasing VDS, you'll find that the current also still increases because you're getting your negatives to be attracted to that positive there of the battery on your VDS. Your VDS there is positive, So you're getting your negative to be attracted to positive. So you still get current flowing, even though the resistance is increasing. Then there's this phenomenon called pinch-off voltage. If VGS is 0 and VDS continually increases to a more positive voltage, a point is reached where the depletion region gets so large that it pinches off the channel. This suggests that the current in channel drops to 0, but it does not. As VDS increases, so does ID. However, once pinch-off occurs, further increases in VDS do not cause ID to increase. A simple analogy to explain pinch-off voltage is if you were to imagine yourself watering a garden, connecting a pipe to the tap, and you're watering a garden, your water is on. Whilst you're busy watering the garden, all of a sudden you're no longer getting output. The first thing that you're going to suspect is that somebody has closed the tap. If you find out that no one has closed the tap, chances are there is a kink. The pipe has been twisted in its length, somewhere along the length of the hose pipe. It's been pinched, it's twisted. Once it's twisted, that kink causes the channel to be narrower, and hence water cannot flow. So with everything else connected, we avoid this situation. This is pinch-off voltage. The pinch-off voltage here, the substrates have come too close to one another, and hence narrowing the passage here. So you cannot get current to flow through. Yet we have enough on the source, and the drain is made positively enough to attract the electrons, but there's obstruction here that talks to pinch-off voltage. It's important that you understand that, because that's one of the parameters that you are given when you're talking about the field effect transistors. It's pinch-off voltage gets specified. That's the voltage at which your output is sunk with everything else being connected. Okay. At pinch-off voltage, any further increase in VDS does not produce any increase in ID. VDS at pinch-off is denoted as VP. So VDS, which is your drain source voltage, is denoted as a pinch-off voltage, because that's where saturation is. You're no longer getting an increase in your ID because the passage has been obstructed. ID at saturation, or the maximum ID possible in your circuit, is referred to as IDSS. I did mention that one of the differences between a PJT and a field effect transistor is that you remember that your IC for BJTs is given by beta IB. So there's a linear kind of a relationship in your controlling variable and the controlled variable. Whereas with your field effect transistors, ID is given by IDSS into 1 minus VGS V pinch all squared. So your IDSS is nothing else but is ID at saturation. Okay, JFET operating characteristics. As VGS becomes more negative, the depletion region increases. As VGS, your gate source voltage here, as it becomes more negative, so you'll be getting your hole, if it becomes more negative, you'll be getting your holes to be attracted to this negative, leaving behind electrons. So your depletion region gets bigger, and as it gets bigger, it makes the passage to be narrower. So eventually we'll arrive at VDS equal to pinch-off voltage, and we'll get our output current to be 0. JFET operating characteristics. As VGS becomes more negative, the JFET experiences pinch-off at a lower voltage, okay? ID decreases even when VDS increases. ID eventually drops to 0. the value of VGS that causes this to occur is designated as VGS off. So finally, it will be summed off if the depletion region keeps increasing, resulting into VGS being 0. So that's VGS off. Okay. I will not. Okay, let's pass this one. The N-channel JFET, now we're looking at the symbol of a transistor. That one was a basic, what we looked at was a basic construction, what it looks like in a block form. That was a block form. But the symbol of a JFET N-channel JFET looks like this. That's your transistor there, that's your gate, that's your drain, that's your source. So you have VGS across here. That's the symbol of your transistor. The JFET input-output transfer characteristics are not as straightforward as they are for a BJT. I've mentioned this several times that your input-to-output transfer characteristics for your BJT is that IC is equal to beta IB, which is just simple and straightforward. So BJT, B indicates the relationship between your input current and your output current, and beta is a constant. So there is linear relationship between your IB and your IC. The JFET, the relationship of VGS, which is your input, remember the field effect transistors, your controlling variable is your voltage, controlling your output, which is your current, ID, is a little more complicated. This is what it looks like, and this is the equation that I was referring to, which is Shortley's equation. ID is equal to IDSS into 1 minus VGS over V pinch all squared. That square relationship already suggests a nonlinear kind of a relationship between your controlling variable, which is your VGS, and your controlled variable, which is your ID. So this relationship, it can be represented by a graph. And this graph shows the value of ID for a given value of VGS. We'll indulge on this more when we're doing our chapter 7, which will be a chapter after this. So here, like for instance, you have your VGS against your ID, VGS in volts against ID in milliamps. Here at -4, that's your pinch of voltage. At this voltage, your device will give you an output current of 0, and your maximum possible current is your IDSS. In this case, it's 8 milliamps. But we're still going to look at that in depth in the forthcoming chapter. Okay, plotting the JFET transfer characteristic curve using IDSS and VP, which is a pinch of voltage, which can also be synonymously called as VGS off. Values found in a specific sheet. The transfer curve can be plotted according to these 3 steps. The transfer curve is plotted according to these 3 steps. Your VGS is 0, ID is equal to IDSS, so it's saturated. As you saw on that slide where I showed you ID being saturated, being 8 milliamps, and then you solve for VGS equal to VGS off, which is a pinch of voltage. On the previous slide, it was showing as -4. Okay, but we'll do that more on the forthcoming chapter. So that's a specification sheet for your JFET. Let's go past that one. Also that one, let's just pass it. And then that was a JFET. I said there are 2 main categories of field effect transistors. You have a JFET, which is split into 2, can either be an N channel or a P channel JFET. And then we have MOSFETs, we have two different types of MOSFETs. They have characteristics similar to those of a JFET and additional characteristics that make them very useful. These types are your depletion type MOSFET and your enhancement mode MOSFET. There's the block representation of your depletion type MOSFET. You have a P substrate there. And then we have an N-doped regions, which is here. Okay, and you have your silicon oxide. And you have your metal contacts there, which are your drain, your gate, and your source. The drain and source connect to the N-type regions, which is here. These N-type regions are connected via an N channel. This is the channel where you get your electrons to flow from the source to the drain. That's your channel there. This N channel is connected to the gate via a thin insulating layer of silicon dioxide, which is this one, shaded here. That's your silicon dioxide. Then the N-type material lies on a P substrate that may have an additional terminal connection substrate. That's your external connection substrate. That's a basic construction of a depletion type MOSFET. So that's your N channel here. So this one is an N channel depletion type MOSFET. Okay. It can operate in, so the MOSFET, as I've said, it can operate as in a depletion mode or an enhancement mode. Oh, sorry, where were we? Okay. And then the characteristics of a depletion type MOSFET are similar to a JFET in a sense that your ID, which is the output current, is given by Shockley's equation, given by IDSS into 1 minus VGS over V pinch all squared. So it's similar to a JFET that we saw previously. And then the enhancement mode MOSFET, that's the one that I said it doesn't have a pre-existing channel, it gets enhanced. Okay. That's a P channel depletion type MOSFET. You see now it has changed. The substrate was a P on the N channel. Now it's reverse. We have an N material as a substrate, and now the channel is a P, and everything else is still the same. You have a silicon dioxide there, and your metallic contacts which give you your drain, your gate, and your source. The symbol of a depletion type MOSFET, that's what it looks like. And channel, that's a symbol with the arrow pointing in on the substrate, that's your N channel. With the arrow pointing out on your substrate, that's your P channel depletion type MOSFET. That's the data sheet. Let's not worry about that one. Enhancement mode MOSFET. The drain, which is symbolized by D, your source, connect to the N-type regions. These N-type regions are connected via an N channel. Okay, so we have your N-doped region there. Can you see now we don't have a channel? There's no connection between the N-doped regions. That's why I said this one does not have a pre-existing channel, but it gets enhanced externally through the connection of your batteries. We create it artificially, hence the name enhancement mode MOSFET as compared to the depletion. So the major differences between the two MOSFETs, the depletion type MOSFET and the N-channel MOSFET, is that the depletion type MOSFET does have a channel, whereas the enhancement mode MOSFET does not have a pre-existing channel. It gets enhanced. The gate connects to the P-type substrate via a thin insulating layer of silicon dioxide. Yes, there's your silicon dioxide, there's your gate. There is no channel, which is what I've just mentioned. The N-type material lies on a P-type substrate that may have an additional terminal connection called the substrate. We do have the substrate here. Okay. So mainly, that's the main difference between a depletion type MOSFET is that a depletion type MOSFET has a pre-existing channel, whereas the enhancement mode MOSFET does not have a pre-existing channel. Operation of an enhancement type MOSFET. VG is always positive. As VGS increases, ID increases. VGS, remember, it's our controlling current, it's our controlling voltage, because the field effect transistor is a voltage controlled device. As VGS is kept constant and VDS is increased, then ID saturates. ID will saturate, it will not increase anymore. It reaches a level where it just saturates, and that level we've already established that is called IDSS, which is ID at saturation. Okay. Sorry. Okay, all right. Then it's transfer characteristic curve. The transfer characteristic curve, to determine ID given VGS, ID is equal to K, which is some constant, equal to VGS minus VT all squared. This VT voltage is a deciding voltage. It's a voltage below which your transistor switches off and a voltage above which your transistor switches on, hence the name threshold. And K is a constant which is given by a specific point, and it's determined by using the values at a specific point, and the formula that gives you K is your ID on over VGS on minus V threshold all squared. For your enhancement mode MOSFET, you'll always be given your VGS threshold, which is a minimum voltage that decides whether your transistor is going to switch on or off. Also, you'll be given this point where your VGS is on and its corresponding coordinate of ID on. So you'll be given this too. Hence, you'll be able to find your K, and after finding K, you'll be able to establish what your ID is, okay? This is a P-channel enhancement mode type MOSFET. The substrate there is N. Okay, so you have a P there and a P there, and you don't have a pre-existing channel again, and then the rest is the same. So the P-channel enhancement type MOSFET is similar to its N-channel counterpart, except that the voltage polarities and current directions are reversed. Yes, of course. If it's a P-channel and an N-channel, the only difference will be in terms of your how you connect your batteries. So your polarities will be reversed. And then that's a MOSFET symbol. Can you see now? It doesn't have a continuous line there, like is the case for your depletion type MOSFET. Instead, it's broken. But with your arrow going in, that's your N-channel enhancement mode MOSFET. arrow coming out, that's your P channel enhancement mode MOSFET. Don't worry about the specification sheet. Electrical characteristics, don't worry. Of the more sensitive to static electricity. So they're very, even if we are working with it, it's very sensitive to static. So you need to de-energize yourself because our bodies are conductive. So it's very sensitive to static. Hence, it's not as robust as your JFET. Okay, MOSFETs are very sensitive to static electricity because of the very thin silicon dioxide layer between the external terminals and the layers of the device. Any small electrical discharge can create an unwanted conduction. So for protection, always transport in a static sensitive bag. Always wear a static strap when handling MOSFETs. Apply voltage limiting devices between the gate and the source, such as back-to-back Zenas. Yes, if you are working with the MOSFET, you would have to wear a static strap. For those of you who are already in industry and have worked with this component, they understand exactly what do I mean. That static strap de-energizes you, so then we are safe to work with the MOSFETs. Okay, VMOS is not part of our scope, but it's good to know that there is a VMOS. A VMOS is a vertical MOSFET. It's a component structure that provides greater surface area. Advantages of a VMOS devices handle higher currents by providing more surface area to dissipate heat. VMOS devices also have faster switching times. As a vertical MOSFET, it's faster. Then we have a CMOS, which is a complementary MOSFET. Uses a P channel and an N channel MOSFET, often on the same substrate as shown. Advantages: useful in logic circuit design. So for your digital application. And is higher input impedance, faster switching speeds, lower operating power levels. That's your CMOS. Okay, the summary looks like that. In a nutshell, that's your JFET there. Okay. And then over there, we have a depletion type MOSFET and channel because the arrow goes in. And then we have our enhancement mode MOSFET and channel enhancement mode MOSFET because the arrow goes in. Again, you notice that the relationship of your output current for your JFET and your depletion type MOSFET is the same. ID is given by IDSS into 1 minus VGS over V pinch. Same goes here on the depletion type MOSFET. Except for the enhancement mode MOSFET, where ID is given by K or into VGS minus VGS threshold all squared, with K being given by ID on over VGS on minus VGS threshold all squared. We're going to see this more on the forthcoming chapter where we'll be solving for our output current. Basically, this is the end of chapter 6. It's more of theoretical knowledge. There won't be any calculations on this chapter. So as I've highlighted, that you need to be able to know the structure of each one, be it a JFET, be it an enhancement mode MOSFET in its block form, and be able to bias it, connecting biasing meaning connecting the external battery for it to operate. Just that, and identify its symbols. Know the differences between the BJT and the field effect transistors. Know the similarities as well. Know the differences between the MOSFETs, which is your depletion type MOSFET, and the enhancement mode MOSFET, where I said the depletion type MOSFET has a pre-existing channel, with enhancement mode MOSFET not having a pre-existing channel, but instead it gets enhanced. So it's more theoretically than anything else. So that's the end of our today. Are there any questions for me? So please go through it. If you need me to send you the slides, I will do that. And please go through this chapter in the book. You'll be knowing exactly what to touch on based on today's coming together. Any questions for me?
Sorry, Miss.
Yes.
Hey, Miss, we have a question, Miss. Me and my group, we are doing the tutorial for DC for AC analysis.
AC analysis. Yeah.
Okay. Miss.
Yeah.
When we are giving like they told us that
you know what you should do. You know what you should do. Just send me that problem, then I'll give you the solution. If you cannot unpack it here.
Okay, Miss.
Right? Just send me the problem, and then I'll come back to you with the solution. You can send me an email. Yeah, I'll go through it and come back to you. It's good that you're working on it, because our test 2 will be based on chapter 5, which is BJT AC analysis, and most probably just this chapter only, chapter 6. So it won't be a very long test. It will be pretty similar to test 1, short in that sense. Yeah, so it's good that you're working on it. Any more questions?
Can we please get the slides for chapter 5, Max?
Chapter 5. Okay, I'll send you the slides. In as much as I prefer for chapter 5, for the nature of its for its nature, do tutorials more, because the marks are more in doing. It's more of a problem-solving chapter. It's not like this one. This one, at least, it's more theoretical, so the slides come handy. So the more you do on chapter 5 is the more you understand. It's okay to be confused, because if you get confused and then I help you out of it, you'll never be the same. So it's fine. I will send them, but I prefer you do the tutorial more, because it's a problem-solving chapter. That's the only way you're going to learn and master it. And you have to master it, because it carries a lot of marks. One problem carries a lot of marks, as I demonstrated to you in class.
I understand.
Okay, my dears. Thank you very much. We'll meet again. I've scheduled a meeting for you for project on Wednesday morning. Reason being, I never got time to take you guys, the day group, through the report format. The evening group did get that advantage on Saturday. So I'll just take you briefly on Saturday, just to take you through the report format, just to give you a glimpse of what I expect, of what do I mean by a topic. Like, for instance, if we say acknowledgement, what do I expect to go there? Introduction, what do I expect to go there? So if there are no more questions, we'll meet on Wednesday morning. Okay, thank you very much. Take care.
I'm sorry, ma'am.